So question 10, the decomposition of sulfur trioxide is in dynamic equilibrium. Okay, so there's your reaction. And remember, this is a forward and reverse reaction, and it's at equilibrium. What happens when you change, when the pressure of the system is increased? And there are your four options. Okay, so all the options talk about the position of the equilibrium, okay, and they also talk about the rate of reaction. Now, it's best to consider these two things separately, okay? So let's start with the position of the equilibrium. Now, in this reaction, on our left-hand side, we've got 2 moles, and on our right-hand side, we've got 3 moles, okay? So if we increase the pressure, according to Le Chatelier's principle, the reaction is going to try to oppose that. In other words, to decrease the pressure. So if we increase the pressure, the reaction is going to shift, or the position of the equilibrium is going to shift to the left-hand side, because this is the side with the fewer number of moles, okay? So in terms of position of equilibrium, P, O, E, let's say, that's going to go to the left. That's sure. So now let's look at the effect on the reaction rate, okay? Now, you need to stop thinking about Le Chatelier's principle when we're talking about reaction rate. And I think a few students might make mistakes because they think, okay, well, in terms of reaction rate, then it's also going to be going to it's also going to decrease, because if the equilibrium is going to the left, then you're going to be making less stuff because there's less moles this side, but that's totally the wrong way to think of things, okay? Rate of reaction, we're talking about here the relationship between rate of reaction and pressure, okay? So this is all about particles, and we're not concerned whether we're talking about forward or backward reaction. We're just talking about the rate of reaction. Now, the rate of reaction is going to increase when you increase the pressure, and that is because you're squeezing particles into a smaller space. Let me get an image up to try and help you. Okay, so this image should help. Here we've got a lower pressure, and here we've got a higher pressure. Effectively, what's happening is you're squeezing particles into a smaller space, which means you're going to have more frequent collisions, which means you're going to have more chance of successful collisions. So in other words, if you increase the pressure, regardless of Le Chatelier's principle, you are going to increase the rate of reaction both ways. Okay? Now, just another thing to mention here. This theory only holds firm when you're talking about reactions that involve gases, okay? Because in this reaction we do have all gases. We're talking about this situation here, these guys here at the top, okay? Now it would also increase the rate of reaction if you had a gas and a solid, but if you only had if you only had solids or only had liquids, then the pressure would have no difference on the rate of reaction, okay? So very quick recap, we're going to shift the equilibrium to the left-hand side because that is the side with the fewer number of moles, okay? And that's all about Le Chatelier's principle. And we are going to increase the rate of reaction because effectively we are going to have more collisions and therefore more successful collisions, which will result in an increase in reaction rate. So the answer here is going to be C. The rate of reaction will increase, and the position of equilibrium will move to the left, as I explained up here. Hope that has helped.